Alright, hello. This is a continuation of limits. And ignore the graph right now, we're doing the right side. And the lesson is the properties of limits. And so pretty much, you'll get it. There's nothing really to explain, but you'll get it as we go along. With this problem, you're given a table. I didn't draw a table, but it has these three limits given to you. Limit of f of x as x approaches -1 is 2. Limit of f of x as x approaches 1 is 4. Limit of g of x as x approaches 1 is 6. And so you're asked to find the limit of f of -x plus g of x divided by 2. And so for pretty much what the idea is that when you're dealing with multiple functions, you can treat them separately and take their limits separately. So if we go do this problem, we do limit as x approaches 1 of f of -x plus limit as x approaches 1 of g of x divided by 2. And we can do these separately, then add them after. So we put the 1 in for the f of x, but it's a negative here, so it's the limit as x approaches -1 instead, because it becomes negative. That answer is 2 up here. It's not 4, because the negative x changes what it approaches to -1. So we get 2 on this side, and then plus the limit as x approaches 1 of g of x, which is 6, and it's divided by 2, so 6 divided by 2, and then 2 plus 3, so this answer is 5. Pretty much it's just to show that you can take the limits differently. Okay, now we're onto the graph problem. And we're trying to find the limit of f of x as x approaches 1. And it's kind of weird because it's a function in a function. So where do you start? Well, you start with the inner part. So we can do the limit as x approaches 1, and in this case the inner part is f of x, so let's just do that. For the limit as x approaches 1 of f of x, we can look at the graph. X of x is 1, going down, the limit is -5. And so after this, we already used the limit, so we don't need that anymore. So now we just do f of -5, and -5 at x equals -5, it's 2. So the answer to this problem is 2. You don't use the limit twice at f of x and then at -5, you only use it once. Here, in this case, the limit would also be 2, but that's besides the point. You only use it once. Okay, so the last thing we're going to have to do for this section, I think it's 1.5 or something, I don't know. But anyway, the last thing you have to do here is take a limit using a table. And we're trying to solve this equation, the limit of f of x squared minus h of x minus g of 1 as x approaches 1. And so the first place we start is just we take the limit of all these functions. So we start with f of x. The limit of f of x as it approaches 1, we look at the table, it's -1. So we write down -1, parentheses, that's awful parentheses, parentheses squared, and do minus the limit of h of x as it approaches 1. That is 6, so -6. And then minus, so for g of 1, the number's already given to us, so we do not take the limit. So we do minus g of 1, which is -2. Oh, that's a bad 2. There we go. Now we just solve 1 minus 6 plus 2, -3, and that's the answer. Oh, bad circle. Yeah. That's how you take a limit using a table. It'll never really be that hard. Sometimes it'll be multiplication, but that's about it. Okay, so on to the next lesson. Pretty much, first thing you gotta know is that to find a limit and you're given like the function as you are here, f of 4x squared minus 5x divided by x, you can just substitute the number in to find the limit. So in this case, if we plug in 0 directly, because it's the limit as x approaches 0, it's undefined, so we have to do something. Now the numerator can be factored by an x, so we can do x times 4x minus 5 all over x, and then the x's will cancel. Then you can do the limit as x approaches 0 of 4x minus 5. and then you can just get -5, and that's the answer. You can directly substitute the number in, what number is being approached to solve if you're given the function. But now there's some other stuff you have to know. For some reason, it's these trig functions on Desmos. We'll start with this one. Sine of the limit as x approaches 0 of sine of x divided by x is 1, which you can see here. Even though it says undefined, but it's because it is, but the limit is 1. And what you also have to know is that if you change the numbers of this fraction, it changes the value of the limit too. So let's say you do sine of 2x over x, then the limit's going to be 2. If you do sine of 3x, then the limit's going to be 3. But if you do sine of x divided by 2x, then it's going to be 1/2. The limit's going to be the same. It's going to be the ratio of the x values in the function. So that's what you have to know about that. You also have to know x divided by sine of x is 0. I mean, sorry, not 0, 1, same as last function. But this is also the same as last function, is that if you change the top, it's also going to change the limit by the same amount. So if you do 2x divided by sine of x, the limit becomes 2. If you do 3x divided by sine of x, the limit becomes 3. But if you do sine of 3x, then the limit as x approaches 0 becomes 1/3. And it's the same ratio as the fraction, as the limit as it approaches 0. But for the bottom two functions, that's not true. Now for the bottom two, no matter how you change it, the limits as x approaches 0 is always going to be 0. So that's pretty much it. For the cosine, for these two, the cosine ones, the limit's going to be 0 as it approaches 0. For the top two, the limit's going to be 1 as you approach 0. Wait, I didn't change this back. Oops. The limit's going to be 1 as you approach 0, but you can change the values around and get different answers. So if I were to ask, like, what's the limit as x approaches 0 of 3x divided by sine of x, the answer is going to be 3, which it is. That's what you got to know about that. Okay, for this next part, we're going to talk about what it means for a function to be discontinuous. So most of you know that, like, continuous functions, they fully continue at any point of x. There's a y value, like x squared. This function is fully continuous, has no gaps, no nothing. But there are types of discontinuities like holes, asymptotes, and jumps. And you'll get a hole when you have a function that's a fraction, but when you factor either the top or bottom, one of the factors cancels out. In this case, x plus 1 cancels out. So when I show this function, it looks continuous pretty much all the way through. But at x equals -1, if we just hover over it, it is undefined because there's a hole there. And that's one of the forms of discontinuity, because the function is not fully continuous. There's a hole between two x values. That's what it means to have a hole. The next type of discontinuity is asymptotes. And you'll get this when you can factor the functions, or you can't factor them maybe, but at a certain spot the denominator will equal 0, and you'll create an asymptote. In this case it's at x equals -5. What happens is that the left side and the right side go in different directions, and that's an asymptote pretty much. It happens when, I already said this, but just to reiterate, when the denominator is 0 and nothing cancels with it. And the last type, which you'll only see in a piecewise function, and a piecewise function is when you have multiple functions, like x squared and x in this case, that make up a single function, but for different parts. So in this case, x squared is before x equals 2, and x is after x equals 2. And you can see there's a jump right here from from the x squared part to the x part. That's the only way you can get a jump, really, as far as I'm aware. And that's the only reason for a jump you're going to need to know in calculus, is this, a piecewise function. Okay, we were just talking about discontinuity, but what does it really mean for a function to be continuous at a point? So at a random point at x equals c, the c can be whatever number, like at 1, 2, 3, 4, whatever number. Anyway, at this whatever number for this function to be continuous at this number, let's just say at 1. For this function to be continuous at 1, three things need to happen. One is that f of x needs to be defined. And what this pretty much does is that it stops holes from occurring. Because if we go back to Desmos and throw this one up, f of negative, where's negative 1? Negative 1 is not defined. So that stops holes. But what it doesn't stop though is these weird dots that may be above the hole. It doesn't stop that yet, but it does stop the holes. Next thing that a function has to do is that the limit as you approach c of f of x must exist. Let me just type that. Must exist. And what this stops are jumps. It also stops asymptotes. So if we go back, let's go with the jumps first. Since the limit has to exist, there's not going to be any jumps. So that stops that. It's also not going to be an asymptote because the limit has to exist on both sides here, and it just doesn't happen. So it stops both of those. The only thing left is stopping the hole with a dot. So what we had to stop this is that the limit as f of x approaches f of c has to exist. Oh no, sorry. Ignore what I just said. The limit of f of x as x approaches c has to equal f of c. Let me just write that down so you can see it instead of me saying it. The limit as x approaches c of f of x equals f of c. That guarantees continuity. If a function fails any of these tests, it is not continuous. So in this case, this function has a hole in it, so it is not continuous. But if we take this away, if we take that away, it is still not continuous. If we get rid of this plus 1, it's not continuous. If we get rid of the division entirely, it is continuous. That's pretty much what you gotta know for 1.11. Alright, so the next thing is 1.12, and it's about finding domains. You might have done this already, but let's say you have a function x minus 5 over x plus 1. In this case, x cannot be negative 1, so what this tells us is that the denominator, let me just type it out. Denominator cannot equal 0. That's one of the rules for finding the domains. Second thing is if you have a radical. So let's say you have the square root of 7x plus 3. This cannot be less than, it just can't be less than 0. So radical cannot be less than 0. Otherwise you get a negative number and you get I, and that we don't, not in calc AB. The last thing is logarithms. So let's say you have ln of 2x plus 1, like that. And the logarithm, let me type it out again. The logarithm has to be greater than 0, otherwise it becomes undefined. And that's that. The inner function has to be greater than 0. So let's start from the top. In this case, the denominator cannot equal 0. So what's the domain of this? Domain is negative infinity to negative 1. And then we do that u thing off at negative 1 to infinity. That's how you do the domain for that. Now for the radical, this cannot equal 0. It cannot be less than 0, so we can solve it real quick. Square root of 7x. Wait, why did I do the square root? 7x plus 0, x equals negative 3/7. Then we can solve the domain real quick. it's going to be, we can include negative 3 divided by 7 because it can be 0. From negative 3 over 7 to infinity. And in case you don't know, the bracket means it's included and the parentheses means it's not included. And lastly, for the logarithm, 2x plus 1 equals 0, x equals negative 1/2. So this is from negative 1/2 to infinity, but negative 1/2 isn't included. And that's that. That's how you find the domains of stuff. Okay, the last thing for the unit is identifying vertical asymptotes, which we've already kind of been over, and infinite limits. And so the example problem, that's pretty much the only way to teach it, is this function, x squared plus 2x minus 8 divided by x squared plus x minus 12, and we have to find the vertical asymptote. And so the first thing we're going to do is try to factor it, and it does factor. Most things in this class are going to factor. Factors into x plus 4 and x minus 2 at the top. And then at the bottom we get x plus 4. That was a very bad x. X plus 4 and x minus 3. Now we see that the x plus 4's cancel, so we only have one vertical asymptote at x equals 3, because that makes the denominator 0. At x equals negative 4 is going to be a whole since it cancels. But anyway, this tells us that on a graph, let's just do this. It's a graph. At x equals 3, 1, 2, 3, one side's going to go up, the other side's going to go down. I don't know which side yet. But that's the next question. This is the infinite limits part. The limit as f of x approaches, limit of f of x as x approaches 3 from the left, and it's also going to ask the limit of f of x as x approaches 3 from the right. And in this class, you usually have a calculator, and what you can do is plug in the number, or you can graph it like when doing Desmos right here. And let's see, as x approaches 3 from the right side, it approaches infinity, as you can see. But on the left side, it approaches negative infinity. So let's go back, and let's write them down. So from the right, go back, it approaches infinity. The answer, why did I write an 8? Is infinity for this one. And then for the left side, it's negative infinity. And that's pretty much the whole lesson. And that's it for Unit 1. I believe we are done.